Okay, I'd like to give you an introduction to the kinematic equations. These are equations that we're going to be using basically throughout the semester. We're going to really hit them pretty hard in this chapter and chapter 4, but we're going to continue to use them throughout the semester. So, now one thing I'd like to point out is that these only work if you have uniform motion, that is constant velocity, or if you have constant acceleration. If you don't have constant acceleration, then what you have to think about is using your equation where you're integrating the acceleration to find it. But this will work as long as this is just a single value. Okay, so we're going to start out with the acceleration actually, and we're going to talk about how if you remember the equation for the average acceleration, that's the change in the velocity over the change in time. And we're just going to rearrange this equation. This will give us the final velocity minus the initial velocity over, and I'm just going to leave this change in time as delta t. That makes things a little bit easier. Usually when we're talking about final versus initial velocity, those are different values, but a delta t is pretty constant. So what I'm going to do is I'm going to multiply both sides by delta t. That'll give me delta t times the average acceleration is equal to the final velocity minus the initial velocity. And then I'm going to solve for the final velocity, and that's going to give me the initial velocity plus the acceleration times the change in time. So this is our first kinematic equation. Okay. Also, if you are looking for them, the kinematic equations are given in their entirety on page 47. So if you're looking for these, they're on page 47 at the top. And I'm just showing you where they came from, but we're going to be using them throughout the semester. Okay, the second kinematic equation, we begin with our final position is equal to our initial position plus delta x. Now if you remember, so basically we have an initial position and then we add our change in the position, that gives us our final position. We kind of talked about that. And to use an integral to do this, we take the integral of the velocity as a function of time with respect to time. I'm not using limits on these integrals because I'm just using the form. You'll talk about this in math. This is an indefinite integral because I'm not specifying a particular period. This is true for the function over all time. So that's why there's no t1 or t2. So, so just go with it for now, and if you have any questions, please ask me. All right, now when I'm looking for the final position, we're assuming that this is a function of some particular time. So really x of s, x of f is a function of a time, a final time, right? And so that means when we're looking at our velocity, we want that to also be the final velocity. Okay, so I'm going to rewrite this, and I'm going to actually throw this, well here, let me rewrite it first. So the final position is equal to the initial position plus the integral of the final velocity with respect to t. And now I'm going to take my equation 1 and throw it in for the final velocity. Okay? So that means the final position will be equal to the initial position plus, we're going to have the integral of the initial velocity plus the acceleration times delta t dt. Okay, so far so good. Now when you get into calculus, what you'll find is that these two are considered kind of separate functions, so we can actually integrate them separately. So I'm going to break those up into separate integrals. So I've got the initial velocity dt plus the integral of a delta t dt. Okay, this is going to be the same. Now vi is a function of time, but it's not, we're assuming that it's kind of constant in this case since we're looking at like uniform motion. So the integral of that is just going to be, well, we assume that it's times t to the 0 power. So when we multiply that, we're going to get 1 times v initial times, I'm going to put in delta t to represent the change in time. Because if I had a t1 here and a t2, then this would be delta t, basically. Okay? And now I'm going to have to use my formula to do this, and we're going to treat delta t as if it's just a t. So when we do that and we integrate that term, we're going to have 1/2 a delta t squared. Okay, so the final position is equal to the initial position plus the initial velocity times the change in time plus the acceleration, 1/2 the acceleration times the time squared. Okay, this is our second kinematic equation. All right, now for the last kinematic equation, what I'm going to do is I'm going to kind of go back to that first one, and we had that v final equals v initial plus a delta t, right? And I'm going to actually plug that, or I'm going to solve for delta t first of all. So delta t in this case is going to be equal to v final minus v initial over the acceleration. And I'm going to plug that back into my equation 2. Okay, so I'm going to have the final position is equal to the initial position. And then I'm going to stick in, I'm going to have plus the initial velocity times v final minus v initial over a plus, I'm going to say a over 2 here, and then I'm going to have v final minus v initial over a, and that's going to be squared. Okay. So the first thing I'm going to do is I'm going to multiply through by 2a. Well, actually, the first thing I'm going to do is I'm going to say that I'm going to move this, subtract x of I from both sides. And that means on the left-hand side, I'm going to have delta x. And then I'm going to multiply this through vi times vf minus vi squared over a plus, I'm going to have vf squared minus 2 vi vf plus vi squared over, and now I have an a squared on the bottom and an a on the top, so I'm just going to write this as 2a. Okay. Next, I'm going to multiply the whole equation through by 2a. So on the left-hand side, we'll have 2a times delta x. And on the right-hand side, we're going to have 2 vi vf minus 2 vi squared. Okay. On the right-hand side, since we multiplied by 2a, the whole denominator just goes away. So we'll have plus vf squared minus 2 vi vf plus vi squared. Okay, so hopefully we can see that this term is going to cancel this term, and then this term is going to go away, and we're just going to have a minus 1 vi squared left. So that means 2 times the acceleration times the change in position is equal to the final velocity squared minus the initial velocity squared. And so the final velocity squared will be equal to the initial velocity squared plus 2 times the acceleration times the change in position. And this is our third and final kinematic equation.